This is Root Locus Example 10. So in this problem, like in example 9, all we're doing is we're drawing the root locus for a system. And in this case, we've got a controller, G sub C, and we've got our plant, G sub P, and we have our feedback, which is going to be our H, and so I'll just draw that in. And again, here, H is going to just be 1, understood 1. So in this case, we're going to use a lag controller. So I wrote it here in green. And a lag controller is such that the 0 term, that's the S plus 3, is a larger number. The 3 is larger than the polar term, that's the one down here, and that has an S equal -1. So because the 3 is larger than 1, we call this a lag controller. And that follows the table that I provided during our lecture time for this course. So in any event, that's going to be our control for this system, and we're going to follow the same steps every time to determine what the root locus for this would look like. So we'll start out with just finding the KGH, the open loop transfer function. So KGH, and that's going to be equal to K sub C, or G sub C, which is K sub C, S plus 3 over S plus 1 times GP, which is 1 over S times S plus 10 times H, which is just simply a 1, and that's going to be equal to KC S plus 3 over S times S plus 1 times S plus 10. Okay, and once we have that, we can immediately see the poles and zeros, the starting poles and zeros provided. Okay, now I'll do the closed loop transfer function, and that's going to, of course, be C over R, the output over the input, and that's going to be K sub C S plus 3 over S times S plus 1 times S plus 10 plus K sub C times S plus 3. And if we calculate that through, that's going to be KC times S plus 3 all over S cubed plus 11S squared plus 10S plus KCS plus 3KC. All right, so now the poles and zeros. For the zeros, we have 1, and it's going to be -3. And for the poles, we have 3 at 0, -1, and -10. So once we have that, we can determine the branches of the root loci. It's equal to the number of poles, so there's going to be 3. Okay, now where do the branches exist? Well, I'm going to go ahead and I'm going to draw the pole 0 map here. And we've got a pole all the way out at -10, so -1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's one way out there, so that's right there, -10. We've got a pole at -1, that's right there. We've got a pole at 0, it's right there. And we've got a 0 at -3, so right there. Okay, so let's go ahead and indicate generally where our branches are going to be. In between s equals 0 and s equals -1, there's going to be a branch there because there's an odd number of poles plus zeros to the right of the branch. Between this pole at -1 and this 0 at -3, is there going to be a branch there? In other words, right here in green. And the answer is no, because there are two poles to the right of this green branch. The pole at -1 and the pole at 0. So that one actually does not exist. What about here? And the answer is yes, that branch will exist because there's 1, 2, 3 poles plus 0 to zeros to the right of that. So there does exist a branch there. What about, I'm going to change it to a pink here. What about here? And the answer is no, there isn't a branch there because there's 1, 2, 3, 4 poles plus zeros to the right of that. So that one does not exist. So there are two branches on the real axis as I've shown here in green and yellow. And what I'm going to do is I'm just going to provide this just summary of that. Oops. I guess that's okay there. This is the summary of what we just did. Most people can pick it up from this, but if you do need it, there it is for you. So I'll give you a second to pause this if you want to write that down. But that's where we start with the branches. Now again, it says we have 3 branches, and I only see 2, one at yellow and one at green. But whenever you have 2 poles like this next to each other with a branch between them, that's really going to be 2 branches. Okay? Okay. So we'll keep going. Now we're going to find the asymptotes, and this time I actually included the formula for the sigma sub A, so that's going to be equal to the number of poles, or excuse me, the actual poles, so -0 minus 1 minus 10 minus the zeros, -3, all over the poles, 3 minus the zeros, the number of zeros, 1. So that's going to be -11 plus 3 all over 2, which is -8 over 2, or -4. And gamma, the asymptote angle, and I'll write the general formula here. I'm going to use the other one. Remember, there are 2 formulas, so I'll use the other one for this example than what I used on example 9. But that's going to be plus or minus 2n plus 1 times 180 degrees all over number of poles minus the number of zeros. So that's going to be plus or minus 2n plus 1 times 180 degrees all over 3 minus 1. That's 2. So we can divide the 180 by 2. So that's going to be plus or minus 2n plus 1 times 90 degrees. So for n equal 1, n equals 0, that's going to be plus or minus 2 times 0 plus 1 times 90. So that's going to be plus or minus 90. Just like that. If n equal 1, that's going to be 2 times 1 plus 1. So that's going to be 3. So that's going to be plus or minus 270. And these are identical. Okay. So that's enough. Once we start to see identical things or repeated things, we don't have to do n equal 2. So I'll just put here not necessary. Okay. Oops, that was a C and this is an E. Okay, so now the breakaway points. So I went ahead and just did these, did this for you. I didn't feel like this was really that necessary. We've got the general formula here, and then I went ahead and just did it out for the poles and zeros. So so you can see here for this is sigma b plus the pole, each pole, and the sigma b plus the zeros. And it's summing each of these up. So 1 over sigma b plus 0 for the pole at 0. 1 over sigma b plus 1 for the pole at negative 1. 1 over sigma b plus 10 for the pole at negative 10. And then equals 1 over sigma b plus 3, that's the 0 at negative 3. So this gives you a formula that is not easy to factor unless you multiply each term by all the other denominators so that you can get common denominators and then cancel those out. But when you do some algebra to get from this step to the second step right here, you can see sigma b plus 1 times sigma b plus 3, sigma b plus 10 times sigma b plus 3, and so on, all the way down. And you notice this negative, that's because we took this and moved it to the left side of the equal sign. Okay, so that's great. Gets you a big long honking thing, and if you were doing this by pen and paper, you wouldn't want to write sigma b a million times. So I just changed the sigma b's to x's, and this right here is really just this with all the sigma b's changed to x's, and then I did a little bit of multiplication through to do a couple things in one line. Start to collect terms in this one, all the x, 3's, x cubed, x squared, x, and then combine until you get this expression. Divide by 2 everywhere to get this expression. And then you can use Wolfram Alpha or MATLAB to get the roots of this. And this has a cube term, so there's going to be 3 roots. And those are the 3 roots. So remember what we're finding. We're finding a breakaway point. And with a breakaway point, it's where the root locus breaks away from the real axis. So when you look at that, these 2 roots, even though they work for this expression, they don't satisfy our need. The only one that does is this one here, this negative 0.54. So that's going to be the breakaway point. So at the very end of this, sigma b is equal to negative 0.54. And we can write that in our root locus diagram. Okay? So now we're at the point where we're just going to draw the root locus, and I'm going to do it right here, and it's going to be ugly, and then I'll replace it with a little better looking one probably. But here's the imaginary real axis. Remember, we've got poles all the way out to -10. So -1, -2, 3, 4, 5, 6, 7, 8, -9, -10. So it's right there. So I'll go ahead and do things in red here. So there's the pole at -10. There is a 0 at -3, so -1, -2, -3. It's right there. We've got a pole at -1, and we've got a pole at 0. Okay. So now I'm gonna zoom in on this. Okay. So let's draw in blue, or yeah, we'll pick blue, the sigma sub b's. So the sigma b was located at -0.54, so that's right there. And it's a little over halfway between the one at -1 and the one at 0. Okay? So that's sigma b. You can barely pick it out. In fact, I can probably zoom in just a little bit more here. Okay? So there you go. There's our sigma sub b, and I can even I'll just indicate that as sigma sub b. And then how about if I draw in the asymptote and lines. Now we found those to be, when we calculated those out, we found those to be at -4. So let's see, this is at -3, so it's right there, and it's plus or minus 90. So it's straight up and down. Oops. Guess I can draw better going up than down. Okay, so there's the asymptote, and I'll just go ahead and label, I'll just put sigma sub a there, and the angle is right there, 90 degrees. Actually, that angle should have been on the other side, but I don't want to ram it into get it around that 0 there. So now we're coming to the end where we actually draw the line. So we'll start out with, I'm going to do them a little bit bigger. So we've got a branch between -10 and -3, and it's right there. So there's one of the root locus. Okay. Now I'll pick orange for one of these root locuses, root loci. From this, it's going to go to that breakaway point from the 0, and then it's going to break away up. Okay? Now I don't know where it's going to go, but the asymptote is a clue that at infinity it's going to be tangential to the asymptote line. Now the other one, and I'll do that in, how about I'll do it in pink. So that's going to go to the middle and break away down. And what they're both going to do is something like this. Okay? And I'll change the other one. I'll go back to my orange, and that's going to do this. So you can see we've been given clues about the breakaway. We've been told where the branches are. There's a branch between 0 and -1 and between -3 and -10. The -10 clearly goes to the 0 because poles always want to go towards zeros. And what you need to realize is that there's a 0 at infinity. And down here, I can do it in the right color, there's a 0 at infinity. Okay? Now those zeros don't exist really, right? But these poles, the branches from these poles, that's where they're headed. And they'll at infinity, they'll be right on this asymptote line. Okay? So I do have a little bit better picture. Unfortunately, I don't have a MATLAB picture, but let's see if I can draw this in. But you can see it's a little bit better picture. Actually, it's there. Let me get rid of this stuff. There we go. So you can see, I mean, it's showing you the same things as my figure, but it's maybe a little neater. So once again, in this one, the only difference from this one to the previous one is that we had a 0 added to it. That changed the branch location. We also we calculated the value of the breakaway point, sigma b. Really wasn't that helpful, but I did show you how to do it, but otherwise exactly the same as example 9.